Hi everyone, my name is Ron, and today with my teammate Shantam, Oliver, Simon, Junie, we're going to present on the geostationary satellite orbit control via MPC. Here's a brief overview of our presentation, starting from our motivation and problem to our dynamics MPC and finally results in future work. So to start off with the problem, the space industry is basically shifting from chemical-based engines to electric propulsion for satellite motion, but these electric systems produce smaller thrust forces and thus require closed-loop control to operate well. Our goal is to basically design and simulate a model predictive controller that can optimize this type of satellite's trajectory, specifically the geostationary satellite. Highlight some of the assumptions that we did make, because we did make quite a few. We simplified the dynamics in a two-dimensional space. We modeled the Earth as a sphere and had circular orbits for both the satellite and the moon that started at the 3 o'clock position. And we used a powerful attitude actuation system that allowed us to control the orientation of the satellite relative to its own axis.
Here's a free body diagram of our system. The satellite is oriented tangentially around the Earth's orbit with an orientation psi. The total force acting on the satellite is composed with the satellite's thrusters in both tangential and radial directions and the gravitational force of the Earth, Sun, and Moon. The total force is then decomposed into its x and y components to calculate the acceleration in each axis. For the state constraints, we use inequality constraints to keep satellites within a certain distance from the reference points to ensure that it follows the reference trajectory. And similarly, we kept that velocity within a certain range around the Earth's angular reference velocity. For input constraints, the thrusters in each direction are limited to a maximum output of 0.5 newtons in this direction, and the orientation of the satellite is limited to 2 pi from its starting position.
Next, we will talk about the MPC algorithm. So the first step is to initialize our parameters and then run the constrained finite time optimal control problem of horizon n m times. And then at each simulation step, we're going to recalculate the next step's reference position x and y, x dot and y dot from the reference r and theta dot, and then we will obtain the optimal input sequence u. And here's our cost. We are formulating it as a quadratic. The state dynamics are obtained from the dynamics equation a few slides prior. Both the state and inputs are bounded by max and minimum values. And we have an initial condition for our state as well as a terminal constraint.
We then modeled 2 types of disturbances to see how our controller would handle non-idealized environments. The first, though minor, was disturbance from the sun and the moon, which exert gravitational pull on our satellite. We fixed the sun, and then the Earth-Moon satellite system is so far in the x direction that changes in the y component of force are negligible. The entirety of the sun's gravity force on our model is in the x direction. The moon is closer to the satellite, so we account for both x and y gravity. Knowing the moon takes 28 days to orbit while the satellite only takes 1, we can derive expressions for the angular velocity and position and then force in both the x and y directions. The second disturbance we include is noise. We add Gaussian noise to the x and y state at every time step to see if our MPC still computes the optimal state and input sequence to land a desired trajectory. The next slide shows some simulation results. On the left, our satellite's able to track a target state trajectory using MPC even when disturbances are present. Disturbances in the trajectory are in blue and don't throw the satellite off its target path. It begins at the 3 o'clock position at t equals 0 and terminates there after 1 day. On the right, our MPC also enables the satellite to track omega Earth, a desired angular velocity, up to a 1% margin of error. This is what makes the satellite geostationary.
As one can see from the top 2 plots depicting the satellite's position and velocity, the x and y coordinates oscillate out of phase with one another, which is exactly the behavior we would expect given that the satellite is moving along a circular trajectory in fixed space. We can also expect similar oscillatory behavior from the radial and tangential thrust inputs due to the satellite's rotation about its own axis psi. As seen by the final plot, psi changes by 2 pi radians over the course of a day, just like the Earth's rotation minus some initial offset. In the future, our project could be further developed in many ways. To name a few, we could begin by extending our problem from 2D to 3D space, using elliptical orbits rather than modeling them as spheres, and additionally invoke a more realistic input by using the angular velocity or acceleration of the satellite's rotation, rather than the angle psi itself. Despite these improvements, we believe that by beginning with a very simple model, we have demonstrated that our MPC design is effective in its reference tracking capabilities and robust in the face of disturbances and noise. Thank you very much.